Hello, ladies and gentlemen. My name is Alexander, and I'm glad to introduce you the article Diffusion Patterns of Social Network Posts. A little bit about me. I'm Gubanov Alexander, and I work as an analyst in Center of Applied Analysis of Big Data at Tomsk State University, Russia. I graduated as applied mathematician and I have experienced as a mathematician, software developer, university teacher, mechatronic inventor, and so on. My current field of interest is a complex network analysis. Now about my team. The CABDA is a group of technical specialists and specialists in humanities who apply modern computational techniques, machine learning, network analysis, and statistics in the field of sociology and psychology. You can see some of our projects below. Well, this project devoted to the phenomena of information spreading in social networks. Kontakte is the most popular Russian social network. It's like Facebook was in its best times. Comfortable interface, reasonable newsfeed ordering, and open API. The problem definition is too fuzzy, so the final statements to work with are as follows. Well, the spreading of information approximated by spreading of publication or set of publications. Let me explain what's this. In Kontakte, the publication is a single block of information containing text, image, video, or audio placed on the wall of the user or group. It's two basic actor types in the social network. Each post has an author. It can be user or group. Each actor can make a repost of the existing post and place it on the self wall. All actors have a news feed where they can see publications of friends and publics they are subscribed to. The moment of appearance of the publication in the actor's wall can be observed, and a sequence of pairs, actor ID and time, is known as information cascade. Well, the information cascade described on the right of this slide. We can also combine the sequence of pair with the social graph and get so-called pattern of spreading. Okay, to study the spreading of information should mean the studying of some specific properties affecting the spreading of the information. The opportunity for information to be spread through an actor roughly defined by two factors: the properties of an actor and the properties of information itself. Actor's behavior can also be defined both by its sensitivity to this specific piece of information or by influence of the actor's surroundings, other actors it's subscribed on. That's why the following research question had been formulated. The first, why do people spread the information? Is it because the information is viral by itself, or they just want to support the opinion of their community? The second, what is spreading? Is it a good piece of information everyone likes, or is just first appeared in the right place, that's why it's widely spread? And the third, who are the actors? Can we define whose opinion is really important for others and whose not? The spreading of information in social network is widely studied and has a lot of approaches. They are listed in paper. But there is still no common approach, and each of existing models are good in several situations, but hard to be applied in others. The object we deal with has several specific features that makes most of the basic approaches useless. First of all, we study the spreading of local important information. In the average city with 500 of thousands of population, The event everyone knows about usually has from several dozens to several hundreds reposts. It's not a lot. That's why most machine learning and epidemic approach don't work here. Observed social network is also just partially relevant, and different structural measurements like degree centrality, between centrality, don't work pretty well also. But we still cannot discard the network as completely irrelevant. The last is that there are both observable and unobservable channels of information spreading. We can observe reposts on walls, but we cannot observe private messaging. The first step in studying our local spreading phenomena is to visualize. The technique can be useful for small cascades and also can give us some intuition about an object. The technique of visualization of a cascade is as follows. Each node in the graph is an actor who has a post or repost of the specific piece of information on the wall. Two nodes, source and destination, are connected by directed edge if destination subscribed on source and post on source wall appeared earlier. In this case, the arc between nodes is a possible path of information spreading. Of course, this graph is acyclic. We can use some classic network analysis metrics to detect communities and nodes that are important for information spreading. One funny result, as we can see on the right, actually it's possible to classify memes just by a structural characteristic of the pattern of spreading. The set of cascades can also be visualized, and it helps to find key actors and key paths of information spreading. Indeed, as long as the visual approach is intuitive, it can be used by analysts just as additional instrument that give them some clues about where to search possible information brokers and opinion leaders. The process of spreading is stochastic, so observed features can appear by accident, not by regularity. Thus, we should use a stochastic model and a statistical approach. One of the most popular models of spreading of something in the network is a diffusion model. At large, it can be written like this in bottom left corner. For each connected pair of nodes in the network, such that one of them is infected and another is not, and for every time t, there is a function p, such that infection spreads through the edge during small interval delta t with probability p times delta t. Well, if p is the same constant for every edge, we've got a common SI model of infection spreading. The common SI model is in the bottom left corner, you can see. The model should have as minimum parameters as it's possible, if it is not a machine learning model, of course. And the number of parameters we cannot reduce for our model is 4. First is the infection rate theta, the intensity of diffusion through the observed link. The second is the infection rate through an observed link, rho. We assume that all nodes are connected together by unobserved ties. Third is a conformism kappa. It defines how much the susceptance of an actor depends on how many of its friends are already infected. And the last is obsolescence parameter delta. We need it because in social networks, the older the information on the actor's wall, the less chance that someone will see it. And in the bottom, you can see the equation for model. Well, some preliminary results. The model and the estimation procedure was first tested on simulation. Well, here we consider the model network on the right and simulate a sequence of cascades with the same predefined parameters. We can see that all parameters estimations converge to their true values, so it's possible to estimate our model. I mean, it's principally possible. Of course, each cascade in real life has a different infection rate because it's different pieces of information. But the decay rate could be considered the same for all publication. It does not depend on the content of publication, it just depends on average behavior of those who make posts and those who read newsfeed and so on. Well, it was also shown that infection rate correlates with decay. The observation is obvious because it's a kind of antagonism between how viral the information seems to be and how fast everyone forgets it. That's why the fraction theta by delta is more stable. And that's why this value, the probability of spreading information through edge, actually used in the independent cascade model. It's a popular model for modeling information diffusion. But never mind. However, as shown above, the decay rate can be considered as a property of the network unaffected by what information was published. That's why it could be measured on the set of cascades, and it's the way to separate it from the infection rate. It was also shown that it's very hard to estimate conformism exactly. That's why we removed it from our tests and left for the good future times. But the good news is that if the network is not fully connected, the observable and unobservable infection rates don't interfere with each other. The approach has also been tested on some real data. We got two posts about one theme, the illegal cuttings of Siberian taiga forests. The red one is about shaming illegal cuts. The green one is calling for flash mob to plant new trees instead of cut it. Well, interesting that both posts diffused among the same part of the network and have comparable outbreak, but the diffusion behavior is different. It seems that people tend to spread the negative information through private messaging without manifestation. But the positive nature-saving information is something they are proud to manifest on their walls. So we can see the results seems to be plausible, but of course there is still a lot of work to be done. Okay, and what's next? The first is to finish the testing, of course. The second is to compare our model with some existing models to ensure that it is relevant. And the third is to optimize estimation procedure and to implement parallel calculation. It's necessary because real networks have millions of nodes and parameter estimation process should be optimized for computing clusters. It also should allow to test the model on truly big data in our plans to make an open source Python library for network dynamics, because actually it's not still presented in the web. And the last is to implement estimation of opinion leadership of vertices. It's like a multiplier for each node, which applies to the average infection rate when the node spread information. Well, it should add to a model a lot of parameters, but if we implement the model with parallel calculations on cluster, everything will be okay. And there is also acknowledgement to people and organizations who made this presentation possible. Thanks for them. And thank you for your patience. The end.